Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Before we begin, take a moment to get comfortable, adjust your pillow, let your body sink into wherever you're resting. There's no rush. We have all the time we need. Where in the world are you watching from? A darkened bedroom where the day has finally released you. A quiet corner where you can finally let your thoughts slow down. Wherever you are, you're welcome here. Tonight, we're going to explore something that sounds alarming, but is actually deeply fascinating. The idea that the universe doesn't have the kind of ending we thought it did, and what that really means for everything we know. We'll journey through the strange geometry of space itself, the discovery that shook cosmology to its foundations, and the beautiful, unsettling truth about infinity that scientists are still grappling with today. It's a story that spans the entire history of the universe, from the first fraction of a second to the unimaginable distances between galaxy superclusters billions of light years away. But don't worry, this isn't going to be an anxiety-inducing cosmic horror story. Instead, we'll move slowly and carefully through the observations, the mathematics and the philosophy, taking our time with each concept. We'll explore what infinite really means, why the edge of the universe is stranger than emptiness, and how this discovery actually gives us a more complete picture of our cosmic home. By the end, I think you'll find there's something peaceful in understanding our place in something so vast. If you enjoy these calm explorations of the cosmos, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being here, for returning to these journeys through space and time. So settle in. Let your shoulders drop away from your ears. Take a slow breath, in through your nose, out through your mouth. And let's begin our slow drift through the question of where or if the universe ends. There's nowhere you need to be right now, nothing you need to solve. Just listen and let the story unfold like the universe itself, gradually, inevitably, beautifully. For most of human history, the universe had edges, clear, definable boundaries where things simply stopped. The ancient Greeks imagined crystalline spheres, nested one inside another, with the stars fixed to the outermost sphere like jewels on a rotating dome. Beyond that final sphere, nothing, not empty space, literally nothing, a concept so foreign it hurt to contemplate. This was a universe you could theoretically measure, finite, contained, comprehensible. Even as our understanding expanded, we clung to this comfort of boundaries. When Copernicus removed Earth from the centre, we simply relocated the edges further out. When Galileo's telescope revealed that the Milky Way contained multitudes of stars invisible to the naked eye, we imagined those stars filling a larger sphere, but still a sphere. A bigger container, but still something with walls. The human mind seems to require edges, borders, places where one thing ends and another begins. By the early 20th century, most astronomers believed the universe consisted of a single galaxy, our Milky Way, surrounded by infinite empty space. This was actually quite a sophisticated view. The galaxy itself was finite, perhaps 100,000 light-years across, containing perhaps 100 billion stars. But that galaxy floated in an eternal, unchanging void. Space itself went on forever, but matter did not. There was still an edge to the meaningful universe. Even if space itself continued. Then Edwin Hubble changed everything. In 1923, using the 100-inch telescope at Mount Wilson Observatory, he observed what were then called Quote 1, fuzzy patches of light scattered across the sky. By identifying Cepheid variable stars within them, he proved these nebulae were actually distant galaxies, each containing billions of stars, existing millions of light-years beyond our own. In one observation, the universe expanded from one galaxy to countless galaxies, scattered through previously unimaginable distances. But Hubble's second discovery was even more profound. By measuring the light from these distant galaxies, he found they were all moving away from us, not just moving, but receding at speeds proportional to their distance. The farther away a galaxy was, the faster it raced away from us. This wasn't because we were at the centre of some cosmic explosion. Instead, space itself was expanding, carrying galaxies apart like raisins in rising bread dough. Every galaxy was moving away from every other galaxy. This observation led to an inescapable conclusion. If the universe is expanding now, it must have been smaller in the past. Wind the clock backward far enough, and all of space, all of matter, all of energy must have been compressed into an infinitely small, infinitely dense point. The universe had a beginning, what we now call the Big Bang. Suddenly the universe wasn't eternal. It was approximately 13.8 billion years old, born in a moment of incomprehensible violence and expansion. This gave us a new kind of edge, a temporal edge, a beginning in time. And if the universe had a beginning, simple logic suggested it might have an end, both in time and in space. Perhaps the expansion would slow, stop and reverse, pulling everything back together in a big crunch. Or perhaps the expansion would continue forever, but the matter would spread so thin that eventually only cold, dark, isolated particles would drift through an eternal void. Either way, we had boundaries again. Perhaps not boundaries in space, but boundaries in fate. And then we discovered something that rendered all of these comfortable models incomplete. The universe, it turns out, is far stranger than a simple expanding sphere with edges we simply haven't reached yet. Which brings us gently to the heart of what scientists actually discovered. Understanding what scientists discovered about the universe's structure requires understanding light itself, not as we experience it illuminating a room, but as a cosmic messenger that carries information across impossible distances. Every photon of light that enters your eye or strikes a telescope mirror began its journey somewhere else, and the farther away that somewhere is, the longer ago that someone was. Light travels fast, approximately 186,000 miles per second, or about 300 million meters per second if you prefer. This seems instantaneous in our daily lives. Flip a switch and the room floods with light. But this speed, as fast as anything in the universe can travel, becomes tortuously slow across cosmic distances. Light from the sun takes about 8 minutes to reach Earth. From the nearest star beyond the sun, Proxima Centauri, light travels for over 4 years before arriving here. From the Andromeda Galaxy, our nearest large galactic neighbour, light travels for 2.5 million years. This means that when we observe distant objects, we're not seeing them as they are now. We're seeing them as they were when their light began its journey toward us. We see the sun as it was 8 minutes ago. We see Andromeda as it was when our ancestors were still evolving into modern humans. And when we point our most powerful telescopes at the farthest galaxies we can detect, we're seeing them as they existed more than 13 billion years ago, less than 1 billion years after the Big Bang itself. This creates a strange observational horizon. Because the universe is approximately 13.8 billion years old, light from anything more than 13.8 billion light years away hasn't had time to reach us yet. There's a sphere around us with us at the centre, beyond which we cannot see, not because nothing exists there, but because the light simply hasn't arrived. Astronomers call this the Observable universe, a sphere roughly 93 billion light years in diameter. But here's where it gets fascinating. That number, 93 billion light years, is larger than twice the age of the universe times the speed of light. If the universe was static, and light had simply been travelling through unchanging space for 13.8 billion years, the observable universe should only be about 27.6 billion light years across. So why is it more than 3 times larger? The answer lies in the expansion of space itself. Light from a distant galaxy doesn't just travel through space, it travels through space that's continuously stretching. Imagine an ant walking along a rubber band that's being pulled at both ends. The ant walks forward at a constant speed, but the rubber band itself is also stretching, so the distance between where the ant started and where it's going keeps increasing. Similarly, light travels at a constant speed, but the space it's crossing is expanding, stretching the total distance. This means the light we're receiving from the most distant observable galaxies began its journey when those galaxies were much closer to us. As the light travelled toward us, space expanded, stretching the distance between us and the source. The galaxy that emitted that light 13 billion years ago is now, today, roughly 46 billion light years away. The light has been travelling for 13 billion years through an expanding universe, crossing what has become an ever-increasing distance. Now, you might think this expansion would make it impossible for light from very distant galaxies to ever reach us. If space is expanding, wouldn't the light be carried away faster than it can travel toward us? This does happen for the most distant objects. There are regions of space expanding away from us so rapidly that light leaving them will never, ever reach us, no matter how long we wait. These regions lie beyond what's called the cosmic event horizon, and they represent a true edge to what we can ever observe, even in principle, even given infinite time. But here's the profound realization that emerges from all this. The observable universe, the sphere of space from which light has had time to reach us, is not the same thing as the universe itself. The observable universe is just our horizon, our limited view. Beyond it, space almost certainly continues. And this is where our comfortable notion of edges begins to dissolve into something far more subtle and strange, something we'll explore as we continue deeper into this cosmic mystery. Before we can understand what the universe is, we need to understand the mathematical framework that describes it, and that framework is Albert Einstein's general theory of relativity, published in 1915. This theory revolutionized our understanding of gravity, space and time, but it also, quite unexpectedly, provided the tools to understand the entire universe's structure and fate. Newton's earlier theory of gravity described it as a force acting between masses across space. The Earth pulls on the Moon, the Sun pulls on the Earth, and so on. This worked beautifully for centuries, accurately predicting planetary orbits and allowing us to calculate the motions of celestial objects with remarkable precision. But Newton's theory had a problem. Gravity acted instantaneously across any distance, which seemed to violate the natural speed limit Einstein had discovered with his special theory of relativity. Nothing, not even information, can travel faster than light. Einstein's solution was radical. Instead of gravity being a force, he proposed that mass and energy curve the fabric of space-time itself. Imagine placing a heavy ball on a stretched rubber sheet. The ball creates a depression, and if you roll a smaller ball nearby, it will spiral around the depression, not because the heavy ball is pulling on it, but because the shape of the sheet itself guides its motion. Similarly, massive objects like stars and planets curve space-time, and other objects follow the straightest possible path through this curved geometry. What we experience as gravity is actually the result of moving through curved space-time. The mathematical equations Einstein developed to describe this curvature are elegant but extraordinarily complex. They relate the curvature of space-time at every point to the distribution of mass and energy at that point. In simplified terms, they say, tell me how matter and energy are distributed, and I'll tell you how space-time curves. Tell me how space-time curves, and I'll tell you how matter and energy move through it. It's a beautiful, self-consistent loop. Now, Einstein originally imagined applying these equations to local systems, the curvature around a star, or the orbit of Mercury around the Sun. But mathematicians and physicists quickly realized you could apply these equations to the universe as a whole. What if you treated the entire universe as a single system and asked what Einstein's equations predict about its overall structure and evolution? The first person to seriously attempt this was a Russian mathematician named Alexander Friedmann. In 1922, even before Hubble discovered the expansion of the universe, Friedman found solutions to Einstein's equations that described a universe that was either expanding or contracting. He discovered that a static, unchanging universe was actually unstable according to Einstein's mathematics. Any tiny perturbation would cause it to begin either expanding or collapsing. Einstein himself initially resisted this conclusion. He added an extra term to his equations, called the cosmological constant, specifically designed to allow for a static universe. He later called this his greatest blunder, though interestingly, the cosmological constant has made a comeback in modern cosmology for entirely different reasons, as we'll discover. A Belgian priest and physicist named Georges Lemaître independently reached similar conclusions to Friedman and went further. In 1927, Lemaître proposed that if the universe is expanding now, it must have been smaller in the past, and if you extrapolate backward, it must have begun from what he called a quote 3, a single point containing all the matter and energy of the universe. This was the first clear articulation of what would later be called the Big Bang theory. When Hubble published his observations of galactic redshifts in 1929, confirming that the universe was indeed expanding exactly as Friedman and Lemaître's mathematics predicted, the theoretical framework was already in place. The equations were ready for the observation. This is one of the most beautiful moments in scientific history. Pure mathematical reasoning, starting from first principles about the nature of gravity and space-time, correctly predicted the behaviour of the entire universe before observations confirmed it. But here's where it gets particularly relevant to our question about edges and endings. These same equations, this same mathematical framework, make specific predictions about the geometry of the universe, whether space itself is curved or flat, whether it's finite or infinite, whether it has boundaries or extends forever. And testing those predictions required observations of stunning precision, measurements that would take decades to achieve and would ultimately reveal something unexpected about the very shape of everything we know. Einstein's equations allow for three fundamentally different geometries for the universe as a whole, each with profoundly different implications for its size, its fate, and whether it has edges. Understanding these three possibilities requires thinking about dimensions in unfamiliar ways, but the core concepts are beautifully simple, and they matter deeply to our question about how the universe ends. The first possibility is called a closed universe, or sometimes a spherical universe. Imagine the two-dimensional surface of a balloon. If you're a being living on this surface, unable to perceive the third dimension, your universe seems to extend indefinitely in all directions. You can travel north, south, east, or west forever. Yet the surface is finite. If you keep travelling in one direction, you'll eventually return to where you started. There are no edges, no boundaries, yet the total area of the surface is limited. Now, extend this analogy to 3 dimensions. A closed universe would curve back on itself in a higher dimension we can't directly perceive, just as the balloon surface curves through the third dimension. In such a universe, space would be finite but unbounded. You could travel in any direction forever without hitting a wall, but the total volume of space would be limited. If you somehow travelled far enough in one direction, you'd eventually arrive back where you started. Though the distances involved would be so vast this could never actually happen before the heat death of the universe. The geometry of a closed universe also determines its fate. In such a universe, gravity would eventually overcome the expansion. The universe would reach a maximum size, then begin to contract, accelerating faster and faster until everything collapsed back into a singularity, the Big Crunch. Time itself would have an ending to mirror its beginning. Every galaxy, every atom, every photon of light would be compressed back into infinite density and temperature. It's a universe with both a birth and a death. The second possibility is called a flat universe. This is harder to visualize because we're not talking about flat like a sheet of paper. We're talking about a 3-dimensional space where the rules of Euclidean geometry work perfectly. In flat space, parallel lines never meet, The angles of triangles always sum to 180 degrees, and the circumference of a circle is always exactly 2 times pi times its radius. More importantly, flat space extends infinitely in all directions. Travelled in any direction, you would never, 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 never. Nap 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 never 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 travelled in any direction. You would never return to your starting point, never reach an edge. You would simply encounter galaxy after galaxy, supercluster after supercluster, forever. In a flat universe, there is no spatial boundary, no place where space stops. The universe doesn't end, it just continues, eternally. The fate of a flat universe depends on the balance between expansion and gravity. In the simplest models, a flat universe would expand forever, but the expansion would gradually slow down, approaching, but never quite reaching, zero. Galaxies would drift apart eternally, but at an ever-decreasing rate. Eventually, after incomprehensible spans of time, the universe would become cold, dark, and empty. Not because it collapsed, but because everything spread so far apart that no interaction between particles would be possible. Heat death, rather than crunch. The third possibility is called an open universe, or sometimes a hyperbolic universe. Its geometry is saddle-shaped. If you could somehow visualize it, it would curve away from itself in all directions, like the shape of a Pringle chip but extended into 3 dimensions. This is even harder to visualize than the closed universe, but the key property is clear. Like the flat universe, it extends infinitely in all directions. An open universe would expand forever and accelerate as it does so. Gravity would never slow the expansion enough to stop it. The space between galaxies would grow faster and faster, and the universe would become increasingly sparse, cold, and isolated. Like the flat universe, it has no edges, no boundaries, but it has even less hope of any cosmic scale connection persisting into the far future. For decades, determining which of these 3 geometries describes our actual universe was one of the central questions in cosmology. The answer depends on the total density of matter and energy in the universe. Too much density, and gravity curves space back on itself, creating a closed universe. Too little, and space curves outward, creating an open universe. Exactly the right amount, what's called the critical density, produces a flat universe balanced perfectly on the knife edge between closing and opening. Measuring this density with sufficient precision to determine which geometry we inhabit required observations of extraordinary sophistication, and the answer, when it finally came, was both confirming and deeply puzzling in ways that would reshape our entire cosmological model. The key to determining the universe's geometry came from observing the oldest light in existence, radiation that has been travelling through space for more than 13 billion years, since the universe was just 380,000 years old. This ancient light is called the cosmic microwave background, and it's perhaps the most important cosmological discovery of the 20th century, a gift from the universe's infancy that tells us about its shape, its contents, and its fate. In the first moments after the Big Bang, the universe was unimaginably hot and dense, a roiling plasma where matter and energy were indistinguishable, where no atoms could form because any that tried were immediately torn apart by violent collisions. Photons of light couldn't travel freely through this plasma. They were constantly absorbed and re-emitted by charged particles scattered in every direction. The universe was opaque, like being inside a dense fog that glows from its own heat. As the universe expanded, it cooled. After about 380,000 years, it had cooled enough, to about 3,000 degrees Kelvin, for electrons and protons to combine into neutral hydrogen atoms. This moment is called recombination. And it had a profound effect. Suddenly photons could travel freely through space without being scattered. The fog cleared. The universe became transparent. Those photons have been travelling through space ever since, streaming in every direction, filling the entire universe with this ancient light. Because the universe has continued expanding since recombination, the wavelength of this light has been stretched by the expansion of space itself. What began as visible and infrared light has been redshifted, stretched into the microwave portion of the electromagnetic spectrum. Today, This radiation has a temperature of just 2.7 degrees above absolute zero. It's incredibly faint, but it's everywhere, coming from every direction in the sky, a whisper from the universe's childhood. This cosmic microwave background was first detected accidentally in 1964 by Arno Penzias and Robert Wilson, who were trying to eliminate a persistent noise in a radio antenna they were using for satellite communications. No matter what they did, cleaning the antenna, removing pigeon droppings, pointing in different directions, they couldn't eliminate this faint hiss of microwave radiation. They had discovered the afterglow of the Big Bang, though it took consultation with theoretical physicists to realise what they'd found. The discovery Before we continue, I want to pause for just a moment, because what you have learned in the last 30 minutes is something genuinely rare. Most people move through their entire lives without ever stopping to understand the world at this level, but you did. Tonight you chose curiosity over noise and depth over distraction. That is exactly who this channel was made for. If you want to keep being that person, a like and subscribe takes 2 seconds and make sure this channel never stops finding you. Now, let's go deeper. The discovery confirmed a key prediction of Big Bang cosmology, but it was the detailed measurements of this background radiation that would prove even more valuable. The cosmic microwave background isn't perfectly uniform. It has tiny temperature fluctuations, variations of about 1 part in 100,000. These fluctuations represent density variations in the early universe, regions that were slightly more or less dense than average. These tiny differences were the seeds of all cosmic structure. They would eventually grow through gravitational attraction into the galaxies and galaxy clusters we see today. By measuring these fluctuations with exquisite precision, scientists could determine the geometry of the universe. Here's why. The size and pattern of the fluctuations depend on the curvature of space. In a closed universe, space curves back on itself, making distant structures appear larger in the sky than they actually are, like looking through a magnifying lens. In an open universe, the opposite happens. Distant structures appear smaller. In a flat universe, you see objects at their true angular size. NASA's Wilkinson Microwave Anisotropy probe, launched in 2001, mapped the cosmic microwave background with unprecedented precision. The data it returned was analysed exhaustively, and the answer was clear. The universe is flat, or so close to flat that any curvature is too small to detect with current instruments. The total density of matter and energy in the universe is almost exactly equal to the critical density. Space is Euclidean on the larger scales. This was a definitive answer to a question that had been debated for decades, but it raised an immediate puzzle. Why is the universe so precisely flat? According to our models, the universe should have become either strongly closed or strongly open very quickly after the Big Bang. Remaining this close to flat for 13.8 billion years requires the initial conditions to have been tuned to extraordinary precision. Flat to within 1 part in 10 to the 60th power in the first moments. This seems suspiciously unlikely, a cosmic coincidence that demanded an explanation. And there's something else this measurement tells us. Something that directly addresses our question about edges and endings. If the universe is flat, it's almost certainly infinite in spatial extent. There's no edge out there in space, no boundary where things stop. The universe doesn't end in the sense of having a wall or a limit. It just continues, galaxy after galaxy, stretching on forever in all directions. And that raises a question that's even stranger than wondering where the universe ends. How do we make sense of infinity? Infinity is one of those words we use casually, almost carelessly, without pausing to consider how profoundly strange the concept actually is. We say things will take an infinite amount of time, or describe infinite possibilities, but when we're forced to truly contemplate what infinity means, not as a metaphor, but as a literal description of reality, the human mind encounters something genuinely difficult to grasp. And yet, if the universe is flat, infinity isn't an abstraction. It's where we live. Mathematicians distinguish between different kinds of infinity, but let's start with the simplest concept, an infinity of extent, of spatial continuation. Imagine counting 1, 2, 3, 4, and so on. You can always add one more. There's no largest number, no point where you must stop. The integers, the whole numbers, continue forever. This is called a countably infinite set. Now imagine space itself extending infinitely, no matter how far you travel in any direction, north, south, up, down, any vector you can imagine. There's always more space beyond. You never reach a boundary, never encounter a wall or an edge. There's no frame of reference where you're at the end of space looking out at nothingness. Space just continues, uniformly, eternally, in all directions. This is the implication of a flat, infinite universe. The philosophical implications are staggering. In an infinite universe with matter distributed roughly evenly throughout, there must be an infinite number of galaxies, an infinite number of stars, an infinite number of planets. And if the laws of physics are the same everywhere, which all our observations suggest they are, then given infinite space and infinite opportunities, every possible arrangement of matter that can occur will occur, not just once, but infinitely many times. This leads to conclusions that sound like science fiction, but are actually straightforward logic. In an infinite universe, there are infinitely many planets exactly like Earth. Infinitely many versions of you reading these exact words right now. Infinitely many versions where you made different choices, where history unfolded differently. This isn't speculation or multiverse theory. This is simply what infinite space with finite possible arrangements mathematically requires. Your instinct might be to reject this as absurd. Surely there's only one you, one Earth, one specific configuration of atoms that makes up your consciousness and experience. But consider, matter is made of atoms, and atoms come in a limited number of types. The possible arrangements of atoms in any finite volume of space, while astronomically large, is still finite. Given infinite space, infinite volumes, these arrangements must repeat. The numbers involved are incomprehensible. Perhaps you'd need to travel 10 to the power of 10 to the power of 29 meters to find an identical copy of our observable universe region. But in true infinity, that distance is nothing. There are infinitely many such regions. This creates a strange situation with causality and identity. Those other versions of you exist. They must, mathematically, but they're so far away that light from them will never reach you. They exist beyond the cosmic horizon, in regions of space that are expanding away from us so rapidly that no information, no light, no influence can ever cross between here and there. They're real, but completely disconnected from your reality in any way that matters. Some physicists find this comforting. If everything that can happen does happen somewhere, then in a sense nothing is lost. Every possibility is realized. Other physicists find it deeply unsettling, a challenge to our notions of uniqueness and identity. If there are infinite copies of you, in what sense are you special or unique? What does individuality mean in a literally infinite context? Perhaps the most philosophically challenging aspect is this. In an infinite universe, the very concept of, quote, 7, quote, or quote 8, quote, becomes questionable. You can never survey it, never know it, never even meaningfully describe it completely. You're forever confined to your local region, your observable patch, with the rest of infinity forever beyond reach. Forever unknowable except as an abstract mathematical consequence of the geometry we've measured. And yet, despite these dizzying implications, the measurement is clear. The cosmic microwave background tells us, with remarkable precision, that the universe is flat. And flat almost certainly means infinite. We don't live in a cozy, finite cosmos with edges we simply haven't reached yet. We live in something far vaster, far stranger. and in many ways far more beautiful, though that beauty is of a kind that requires adjustment to appreciate. As we'll explore next, this infinity creates puzzles that push both physics and philosophy to their limits. The discovery that the universe is flat and likely infinite created deep satisfaction in some ways. We had measured the geometry of reality itself, but it also sharpened an existing puzzle to the point where it could no longer be ignored. This puzzle is called the horizon problem, and it relates to something we've already discussed, the cosmic microwave background radiation. That ancient light streaming toward us from every direction has a temperature of 2.7 Kelvin everywhere we look, and that everywhere is the problem. When we observe the cosmic microwave background, we're seeing light that was emitted when the universe was 380,000 years old, from regions of space that are now about 46 billion light-years away in opposite directions. These regions are separated by roughly 93 billion light-years. But here's the puzzle. These regions have never been in contact with each other. Light from one has never had time to reach the other. They exist beyond each other's cosmic horizons. If two regions have never been in contact, never exchanged light or heat or any form of information, why do they have exactly the same temperature? Why is the cosmic microwave background so uniform? Imagine finding two lakes in remote valleys that have been completely isolated from each other since they formed, and discovering they have exactly the same water temperature, the same chemical composition, the same everything. You'd immediately suspect they must have been connected somehow, must have exchanged water or been fed from the same source. The uniformity demands an explanation. In the standard Big Bang model, without any additional mechanism, different regions of the early universe had no way to equilibrate, no way to smooth out temperature differences. Each region should have had whatever temperature and density happened to result from random quantum fluctuations in the first instance after the Big Bang. We should observe a cosmic microwave background that varies wildly in temperature from one direction to another, a chaotic patchwork reflecting the disconnected nature of causally separate regions. Instead, we observe uniformity to within 1 part in 100,000. Everywhere we look. The temperature is 2.725 Kelvin, with only tiny fluctuations around this average. The universe looks the same in all directions, isotropic, as though it had been carefully smoothed and mixed. But the speed of light, the maximum speed at which information can travel, wasn't fast enough to allow the necessary mixing in just 380,000 years. This puzzle deepens when you consider the flatness we've already discussed. Remember that a flat universe requires the density to be tuned to the critical density with extraordinary precision. In the earliest moments after the Big Bang, this tuning had to be accurate to within 1 part in 10 to the 60th power. Any tiny deviation from perfect flatness would have been amplified exponentially as the universe expanded, starting even slightly closed. The universe should have recollapsed almost immediately. Starting even slightly open, it should have expanded so rapidly that no structures could ever form. Yet somehow, the early universe started with almost perfect flatness. It also started with almost perfect uniformity. These two facts, flatness and uniformity, seem to require initial conditions so finely tuned as to be essentially impossible without some mechanism to explain why. It's not satisfying to say that's just how the universe happened to start. Science seeks explanatory mechanisms, causes for effects. Throughout the 1970s, physicists grappled with these questions. Some proposed that perhaps there was some unknown process in the first moments after the Big Bang that allowed regions to communicate faster than light, temporarily violating what we thought were fundamental limits. Others suggested that maybe the universe had undergone a previous phase of contraction before the Big Bang, during which everything had time to equilibrate. But these ideas were speculative, lacking mathematical rigour or observational support. The resolution to these puzzles came from an unexpected direction, from attempts to understand the behaviour of quantum fields at extremely high energies, energies that would have existed only in the first tiny fraction of a second after the Big Bang. A young physicist named Alan Guth was thinking about the behaviour of the Higgs field, the field that gives particles their mass, in the context of grand unified theories that attempted to unify all the fundamental forces. What Guth realised in December of 1979 was that in certain conditions a quantum field could have negative pressure. It could push outward on space itself. And if this happened in the early universe, even for a tiny fraction of a second, the consequences would be dramatic. Space would expand exponentially, doubling in size repeatedly in minuscule time intervals. This brief period of exponential expansion would solve both the horizon problem and the flatness problem in one elegant mechanism. He called this idea inflation. And while it started as a speculative solution to technical problems in cosmology, it would grow into one of the most successful and profound theories in all of physics, with implications that extend far beyond solving the puzzles that inspired it. Inflation doesn't just explain why our universe is flat and uniform. It may also explain why it exists at all, and why there might be far more to reality than the single universe we observe. But to understand inflation, we need to think carefully about what it means for space itself to expand. We've talked about the expansion of the universe several times now, but it's worth pausing to really examine what this means, because it's profoundly different from any expansion we experience in daily life. When we say the universe is expanding, we don't mean that galaxies are moving through space away from each other, like debris from an explosion flying outward through a pre-existing void. We mean that space itself, the fabric of reality, is stretching, and galaxies are being carried along with it. Imagine a ruler. It's a metre long, marked with centimetres and millimetres. Now imagine that the ruler itself begins to grow. Each centimetre mark moves farther from each other centimetre mark. The ruler is still the same ruler, made of the same material, but the space between the marks is increasing. An ant walking along the ruler at a constant speed would find that the mark it's trying to reach keeps getting farther away, not because the ant is slowing down, but because the ruler itself is stretching. This is what's happening with space. Galaxies aren't moving through space. Space itself is expanding, carrying galaxies with it. This might seem like a semantic distinction, but it has profound physical consequences. For one thing, it means there's no centre to the expansion. Every point in space is moving away from every other point. If you were on a distant galaxy looking back at the Milky Way, you'd see us receding just as we see that galaxy receding. Everyone observes themselves as being stationary, while everything else moves away. More importantly, because it's space itself that's expanding, there's no speed limit on how fast distant objects can recede from each other. The cosmic speed limit, the speed of light, applies to motion through space. But there's no limit on how fast space itself can expand. Two galaxies separated by a large enough distance can be receding from each other faster than the speed of a light, not because either galaxy is moving through its local space faster than light, but because the space between them is growing. This is how the observable universe can be 93 billion light-years in diameter, even though the universe is only 13.8 billion years old. Light from the most distant galaxies we can see has been travelling for 13.8 billion years, but during that time, space has been expanding, stretching the distance between where that galaxy was when it emitted the light and where we are now. The result is that the galaxy is now much farther away than 13.8 billion light-years. Now, the rate at which space expands is described by something called the Hubble constant, though quote 10 quote is a bit of a misnomer. It's the current rate of expansion, but this rate has changed over the history of the universe. For every megaparsec of distance between us and a galaxy, that galaxy is receding at an additional 70 kilometers per second. For nearby galaxies, this recession velocity is small enough that their own motion through space, their peculiar velocity, can overcome it. The Andromeda Galaxy, for instance, is actually moving toward us, and will collide with the Milky Way in about 4 billion years, because the local gravitational attraction between our galaxies is stronger than the expansion of space between us. But for distant galaxies, where the expansion accumulates over vast distances, the recession velocity becomes enormous, far exceeding any local motion. The expansion rate hasn't been constant over cosmic history. In the earliest moments after the Big Bang, the universe expanded extremely rapidly, then settled into a gradual deceleration as gravity worked to slow the expansion. For billions of years, the universe was slowing down, and cosmologists debated whether the expansion would eventually stop and reverse, or continue forever at an ever-decreasing rate. Then, in 1998, two teams of astronomers studying distant supernovae made a discovery that shocked the physics community. The expansion of the universe is accelerating. About 5 billion years ago, something caused the expansion to begin speeding up rather than slowing down. This acceleration continues today and appears to be increasing. This was so unexpected, so contrary to what theoretical models predicted, that it took months of careful checking before the teams felt confident enough to announce their results. The cause of this acceleration is something we now call dark energy, a mysterious component that makes up about 68% of the total energy content of the universe. We don't know what it is. It might be a property of space itself. It might be a new kind of quantum field. It might be something even stranger. But whatever it is, it's causing space to expand faster and faster, and it's going to determine the ultimate fate of the universe. This accelerating expansion has profound implications for the far future. Galaxies that are currently within our observable horizon will eventually cross beyond it as the expansion accelerates. They'll recede so quickly that their light will never reach us, even given infinite time. The observable universe will actually shrink in terms of what we can see, even as the universe itself continues expanding. Eventually, every galaxy outside our local group will disappear from view, leaving future astronomers with a much lonelier view of the cosmos. But I'm getting ahead of our story. Before we explore dark energy and the far future, we need to understand inflation, that brief period of exponential expansion in the first fraction of a second after the Big Bang. Because inflation doesn't just explain why the universe is flat and uniform, it also suggests something remarkable about the nature of space itself, something that brings us back to the question of infinity and edges in the most unexpected way possible. Let's travel back to the very beginning, to a time so early that clocks measuring ordinary seconds become meaningless. We need to think in units of Planck time, 10 to the minus 43 seconds, the smallest interval of time that has any physical meaning in our current understanding of physics. The universe is unimaginably hot and dense, existing in a state where quantum mechanics and gravity are equally important, a regime we still don't fully understand because we lack a complete theory of quantum gravity. Then, at approximately 10 to the minus 36 seconds after the Big Bang, that's a decimal point followed by 35 zeros and then a 1, something remarkable happens. A quantum field, possibly the same field that would later be called the inflaton field, finds itself in a high-energy state, a false vacuum. Think of a ball sitting on a plateau on a mountainside. It's in a stable position for the moment, but it's not in the lowest possible energy state. There's a valley below where the ball could roll and settle into a lower, more stable position. In this false vacuum state, the quantum field has negative pressure. Instead of pulling things together like gravity, it pushes outward on space itself. This negative pressure creates a repulsive gravitational effect. Gravity in this regime acts as an anti-gravity force, and because the energy density of this field remains constant even as space expands, the repulsive effect doesn't diminish. More space means more of this field, means more repulsion, means even faster expansion. The result is exponential expansion. Space doubles in size, then doubles again, in intervals of about 10 to the minus 37 seconds. This doesn't sound like much until you calculate how many doublings occur before the field finally transitions to its lower energy state and inflation ends. Current models suggest somewhere between 60 and 100 doublings, depending on the specific details of the inflationary potential. Let's think about what 60 doublings means. Start with any size you like, say something smaller than a proton. Double it, still unimaginably small. Double it again, still smaller than an atom. But keep going. After 10 doublings, you've increased size by a factor of 1,000. After 20 doublings, a factor of 1,000,000. After 30 doublings, 1,000,000,000. After 60 doublings, you've increased size by a factor of 2 to the 60th power. That's approximately 10 to the 18th, 1,000,000,000,000,000 times larger. In inflation, a region of space smaller than a proton expanded to larger than the observable universe today. All in less than 10 to the minus 32 seconds. That's a trillionth of a trillionth of a trillionth of a second. During this brief instant, the universe grew by a factor of at least 10 to the 26th, 1 followed by 26 zeros, possibly much more, depending on exactly when inflation ended. This exponential expansion solves the horizon problem beautifully. Before inflation, the entire region that would become our observable universe was much, much smaller. Small enough that all parts of it were in causal contact, able to exchange energy and reach thermal equilibrium. Inflation then stretched this tiny uniform region to enormous size. The apparent disconnection of distant regions we observe in the cosmic microwave background is an illusion created by inflation. They were once close enough to communicate before inflation drove them apart. Inflation also solves the flatness problem. Any initial curvature of space is flattened by the expansion, much like how the surface of a balloon appears flatter and flatter as the balloon inflates. If you expand a curved space by a factor of 10 to the 26 or more, any detectable curvature becomes immeasurably small. After inflation, the universe would be flat to extraordinary precision, regardless of what geometry it started with. But inflation does something even more remarkable, something that wasn't part of the original motivation, but emerged as physicists explored the theory more deeply. Inflation creates the density fluctuations that became galaxies. Quantum fluctuations, tiny random variations in the inflaton field at the quantum level, were stretched by the exponential expansion from subatomic scales to cosmic scales. These quantum uncertainties became real. Classical variations in density across space. The variations were tiny, about 1 part in 100,000, but they were exactly what was needed to seed galaxy formation. This is one of the most beautiful predictions in all of physics. The structure of the universe, the galaxies and clusters and superclusters, all trace back to quantum fluctuations during inflation. The quantum and the cosmic are connected directly. What began as microscopic quantum randomness became the large-scale structure of the universe. The universe's architecture is, in a very real sense, quantum mechanical in origin. But here's where it gets truly strange. Inflation, by its nature, is hard to stop everywhere at once. Remember, the inflaton field is a quantum field, subject to quantum fluctuations. In some regions, the field might transition to its lower energy state, ending inflation. But in other regions, quantum fluctuations might keep the field in the high energy state, and inflation continues. These regions continue to expand exponentially, creating more space. And within that space are more regions where quantum fluctuations maintain inflation. This leads to a picture called eternal inflation. Once inflation starts anywhere, it never completely stops. It ends in some regions, creating bubble universes, pocket universes, domains where inflation has ceased and normal expansion has taken over. Our observable universe is one such bubble. But beyond our bubble, inflation continues, creating more bubbles, each potentially with different properties, different physics even. And this continues forever, creating an infinite multiverse of bubble universes within an eternally inflating background. This is speculative, and many physicists debate whether eternal inflation is actually what happens, whether it's even a testable scientific theory. But it emerges naturally from the mathematics of inflation combined with quantum mechanics, and it raises profound questions about what we mean by the universe, and whether the question of edges and endings even makes sense in this context. Let's explore these implications more carefully. If inflation is eternal, if it creates bubble universes perpetually, then the reality we inhabit becomes vastly more complex than a single expanding universe. We live in one bubble among countless others, each a universe in its own right, each potentially with different physical laws, different constants of nature, different dimensionality even. This collection of bubble universes embedded in an eternally inflating background is what physicists call the multiverse. The concept makes many scientists deeply uncomfortable. Science relies on testing hypotheses against observations. But if other universes exist beyond our cosmic horizon, forever beyond our ability to observe them even in principle, how can claims about them be scientific? They seem more like metaphysics than physics. Unfalsifiable speculation rather than testable science. Yet the multiverse isn't something physicists invented because they wanted to believe in it. It emerged as an apparent consequence of taking inflation seriously, combined with our best understanding of quantum mechanics. If the mathematics of inflation plus quantum fluctuations inevitably leads to eternal inflation, and if eternal inflation inevitably produces bubble universes, then the multiverse might simply be the way reality is, whether we can observe it directly or not. Consider the logic carefully. Inflation solves real problems: the horizon problem, the flatness problem, the origin of structure. The evidence for inflation is strong, though not yet definitive. We observe a flat universe with tiny density fluctuations matching the predictions of inflation. We observe a cosmic microwave background with exactly the temperature uniformity that inflation explains. The theory works. But if inflation can start, and quantum fluctuations can maintain it in some regions even as it ends in others, then eternal inflation and the multiverse seem to follow necessarily. You can't have the good parts of inflation, the problem solving, the structure formation, without also accepting the implications that make physicists uncomfortable. The mathematics doesn't allow cherry picking. In the multiverse picture, each bubble universe would begin as a small region where inflation ended, but then expand normally, creating its own vast space potentially infinite in extent. Our observable universe, the sphere roughly 93 billion light-years across from which light has had time to reach us, would be a tiny portion of our bubble universe, which would itself be a tiny portion of one bubble, among infinite bubbles in the eternal inflation background. The physical laws in different bubbles could vary. In some versions of inflation, the properties of particles, the strengths of forces, even the number of spatial dimensions are determined by how the inflaton field transitions to lower energy, a process that can happen differently in different bubbles. Most bubbles might have physics that doesn't allow complexity. No atoms, no chemistry, certainly no life. Our bubble happens to have physics that allows stars, planets, and biological evolution. This leads to a controversial idea called the anthropic principle. If the multiverse contains bubbles with every possible variation of physical laws, then observers can only exist in bubbles where the laws permit their existence. We find ourselves in a universe with physics that allows complexity, not because it's the only possibility, but because observers can only arise where such physics exist. The apparent fine-tuning of our universe's constants, the precise values needed for stars to form, for carbon to be created, for chemistry to work, might not need explanation beyond quote, _12, _. Some physicists find this explanation deeply unsatisfying. It seems to give up on finding fundamental reasons for why the constants have the values they do. Others argue it might be the correct explanation, that not all questions have deeper answers, that sometimes quote 1-3 quote is as far as explanation goes. The multiverse also creates strange situations with probability and prediction. If there are infinitely many universes and every possible outcome occurs in some universe, how do you make predictions? How do you say one outcome is more likely than another when both happen infinitely many times? Physicists working on multiverse theories have developed something called the measure problem. Trying to define what probability means in an infinite multiverse, it's a genuinely difficult conceptual challenge, one without clear resolution. For our question about edges and endings, the multiverse picture is both clarifying and perplexing. Our universe, our bubble, likely doesn't have an edge in space. It's either infinite, or if it's finite, it curves back on itself like a balloon surface, with no boundary. But our bubble does have an edge in time. It began when inflation ended in our region. Beyond our bubble, separated by regions where inflation continues, are other bubbles, each with their own beginning, their own expansion, their own physics potentially. There's no edge to the multiverse as a whole, if eternal inflation is true. Inflation creates space faster than that space can expand normally, so the total volume of the eternally inflating region grows without bound. New bubbles form constantly. The process never stops, never reaches an endpoint. In this picture, asking where the multiverse ends is like asking what the largest integer is. The question assumes a boundary that doesn't exist. But this raises a profound question. If the multiverse is infinite and eternal, creating infinite bubble universes, each potentially infinite in extent, what does that mean for our significance, our place in reality? Are we one tiny temporary spark of awareness in an infinite, eternal process that neither began nor will end? Is everything we know and experience cosmically irrelevant, an infinitesimal bubble in an infinite sea? These questions take us beyond physics into philosophy, into the realm of meaning and value. And that's where we're heading next, not abandoning the science, but asking what it means for how we understand ourselves and our place in this strange, vast, potentially infinite reality that the evidence seems to be revealing. We've explored the early universe, inflation, and the possibility of a multiverse, but now we need to return to our own universe, our own bubble, and examine its current state and future trajectory. And here we encounter another profound mystery, one that was discovered only recently, and that fundamentally changes our understanding of what the universe is made of and where it's headed. For most of the 20th century, cosmologists assumed that the expansion of the universe must be slowing down. This seemed obvious. Gravity attracts, pulling everything together, so gravity should act as a brake on expansion. The question was whether gravity was strong enough to eventually stop the expansion and cause a recollapse, or whether the expansion would continue forever, but at an ever-decreasing rate. Either way, deceleration seemed certain. To measure this deceleration, astronomers needed to observe very distant objects with known intrinsic brightness. If you know how bright something actually is, and you measure how bright it appears from Earth, you can calculate how far away it is. Then, by measuring the redshift of the object, how much its light has been stretched by the expansion of space, you can determine the expansion rate at the time the light was emitted. Comparing expansion rates from different epochs reveals whether the expansion is speeding up or slowing down. The ideal objects for this purpose are Type 1, a supernovae, explosions of white dwarf stars that reach a characteristic peak brightness. Because they all explode in essentially the same way, they all reach approximately the same maximum luminosity. They're bright enough to see across billions of light years, and they're relatively common. Two teams of astronomers, the Supernova Cosmology Project and the High Z Supernova Search Team, began systematically observing distant Type 1, a supernova, in the early 1990s. The expectation was that distant supernova, those whose light had been travelling for billions of years, showing us the universe billions of years ago, would appear brighter than expected if the expansion was decelerating. Deceleration means the universe was expanding faster in the past, which means objects at a given redshift would have been closer to us when they emitted their light than they would be in a universe expanding at constant rate. Closer means brighter. But when the data came in, the supernovae appeared dimmer than expected. Not dramatically dimmer, but measurably, consistently dimmer than the deceleration models predicted. At first, both teams suspected systematic errors. Perhaps dust between here and the supernovae was absorbing light, making them appear dimmer. Perhaps the supernovae in the distant past were intrinsically different from nearby ones, not actually standard candles. The team spent months checking and rechecking their data. Finally, in 1998, both teams announced their results. The universe's expansion is not decelerating, it's accelerating. Sometime around 5 billion years ago, the expansion began to speed up, and it's been accelerating ever since. This was so unexpected that when the teams presented their findings at conferences, many astronomers initially didn't believe it, but the evidence was strong, and subsequent observations have only confirmed and refined the result. Something is causing space to expand faster and faster, overcoming the attractive force of gravity. This something is now called dark energy, and it makes up approximately 68% of the total energy content of the universe. Dark energy is not matter. It doesn't clump together, doesn't form structures, doesn't interact with light. It's a property of space itself, a kind of energy density that remains constant even as space expands. The simplest model of dark energy is that it's equivalent to Einstein's cosmological constant, that term he added to his equations to allow for a static universe and later called his greatest blunder. It turns out the cosmological constant might be real after all, but with a very small positive value. In this picture, every cubic metre of space has a tiny amount of intrinsic energy. And as space expands, creating more cubic metres, the total amount of dark energy increases. This increasing dark energy drives the accelerating expansion. But we don't actually know what dark energy is. The cosmological constant explanation is the simplest, but it has problems. Quantum field theory predicts there should be a cosmological constant arising from quantum fluctuations in the vacuum, but the predicted value is vastly larger, 10 to the 120th power larger than what we observe. This is called the cosmological constant problem, and it's one of the worst prediction failures in all of physics. Why is the observed value so incredibly small compared to the theoretical prediction? Alternative models propose that dark energy isn't constant but changes over time, perhaps due to a new kind of quantum field sometimes called quintessence. In these models, the properties of dark energy could evolve, the acceleration could strengthen or weaken. Observations so far are consistent with a constant dark energy, but we can't rule out slow evolution. We're measuring the universe's expansion rate at different epochs with increasing precision, looking for any hint that dark energy is changing. The discovery of dark energy won the 2011 Nobel Prize in Physics. It revolutionized cosmology. Suddenly, the universe's content looked very different than we thought. Ordinary matter, the stuff of stars, planets and people, makes up only about 5% of the universe's total energy. Dark matter, which we can't see but can detect through its gravitational effects, makes up about 27%. And dark energy, which we understand even less well than dark matter, makes up the remaining 68%. We live in a universe dominated by things we don't understand. For the question of how the universe ends, dark energy is decisive. If dark energy truly is constant, the acceleration will continue forever. The universe will expand exponentially into the far future, much like it did during inflation, but at a much slower rate. Galaxies outside our local group will eventually accelerate away from us so fast that their light can never reach us. The observable universe will become increasingly empty and dark. This is a very different kind of ending than the Big Crunch or the gradual heat death we imagined before discovering acceleration. Let's return to a concept we touched on earlier and explore it more deeply, because it's central to understanding what the universe's edges, if any, actually are. The observable universe is the sphere of space from which light has had time to reach us since the Big Bang. It's the portion of the universe we can, even in principle, observe, and understanding its properties and boundaries helps clarify what we mean when we ask about the universe's edges. Remember that light travels at a finite speed, and the universe has a finite age. These two facts combine to create a horizon, much like the horizon you see when standing on Earth's surface. On Earth, the horizon exists because the planet curves away from you. Beyond a certain distance, the curvature of the Earth prevents you from seeing the surface. The cosmic horizon exists for a different reason. Beyond a certain distance, light hasn't had time to reach you yet. But calculating the cosmic horizon is more complex than simply multiplying the age of the universe by the speed of light. Space has been expanding throughout the universe's history, stretching the distance between where light began its journey and where we are now. The current observable universe is approximately 46 billion light-years in radius, even though the universe is only 13.8 billion years old because of this expansion during light's journey toward us. This observable sphere is not the same for all observers. An observer in a distant galaxy would have their own observable sphere centered on their location. Our spheres would overlap significantly, but each of us would see some regions the other cannot. There's no absolute observable universe. It's always relative to the observer's position. Now, the boundary of the observable universe is not a physical edge in space. There's no wall, no barrier, no place where space stops. It's simply the location of the most distant objects whose light has reached us. If we wait longer, light from more distant objects will arrive, and our observable sphere will grow. The observable universe is constantly getting larger as we receive light from farther and farther away. However, there's a complication introduced by dark energy and acceleration. As the universe's expansion accelerates, there are objects that are currently receding from us faster than the speed of light. Light leaving these objects toward us is being carried away by the expansion of space faster than it's travelling toward us through space. Such objects lie beyond what's called the cosmic event horizon, and light leaving them will never reach us no matter how long we wait. The cosmic event horizon is about 16 billion light-years away in terms of proper distance. The actual distance right now between us and objects at this boundary. Objects beyond this horizon are lost to us forever. They exist. They're real. But we'll never see them, never receive information from them, never interact with them in any way. As the acceleration continues, more and more galaxies that are currently within our observable sphere will cross this event horizon and disappear from our view. This creates a strange situation. The observable universe will actually shrink in the far future, not because the universe itself is contracting, but because acceleration is carrying distant objects beyond our event horizon faster than light from new objects can reach us. Eventually, every galaxy outside our local group, the Milky Way, Andromeda, and a few dozen smaller galaxies bound together by gravity, will have crossed the horizon and faded from view. The universe will still exist, still be expanding, but observers like us will only be able to see their own local group. Imagine astronomers in the far future, trillions of years from now. They look out into space with their telescopes and see only their own galaxy, existing in an otherwise apparently empty void. The cosmic microwave background will have redshifted into undetectability. All evidence of the Big Bang, of the expanding universe, of the existence of other galaxies, will have disappeared beyond their horizon. What will they conclude about the nature of the universe? Will they even be able to discover cosmology? This raises profound questions about what we can know and what we might be missing. We're confident we can observe and understand our observable sphere, but what lies beyond it? If the universe is infinite, as flatness suggests, then the observable universe is an infinitesimal fraction of what exists. We're seeing a tiny patch, a minuscule sample. What exists beyond our horizon, beyond what we can ever observe? The honest answer is, we don't know, and we can't know from direct observation. We can use theoretical reasoning. The laws of physics should be the same everywhere. The distribution of galaxies should be roughly uniform on large scales. But these are assumptions, extrapolations. They're well-motivated assumptions. But they're not observational facts. Some physicists argue that science should only concern itself with the observable universe, that questions about what lies beyond are meaningless, or at least scientifically unanswerable. Others argue that if our best theories predict an infinite universe beyond the horizon, we should take that prediction seriously even if we can't verify it directly. It's a debate about the nature of scientific knowledge itself. What's clear is that the observable universe has a boundary, a horizon beyond which we cannot see. This horizon is not an edge of space itself, but rather a limitation on our observation. The universe almost certainly continues beyond it, potentially infinitely. The question of whether the universe has edges becomes entangled with the question of what we can know, what we can observe, and what lies forever beyond our reach. And that's a question with both scientific and philosophical dimensions, which we'll explore as we continue. Beyond our observable horizon lies a realm that is, by definition, unobservable. We cannot see it, cannot receive light from it, cannot detect any signals or information from it. And yet, if the universe is truly infinite, this unobservable region is infinitely larger than what we can see. Everything we've ever observed, every galaxy and star and planet, exists in a finite bubble, surrounded by an infinite expanse we'll never access. This is a strange and humbling realization. Let's think carefully about what might exist in this unobservable realm. Our best understanding suggests that the laws of physics are the same everywhere, that gravity works the same way at the far side of the universe as it does here, that atoms behave identically, that light propagates at the same speed. This assumption, called the cosmological principle, states that the universe is homogeneous and isotropic on large scales. It looks roughly the same everywhere and in all directions. If the cosmological principle is correct, then the unobservable region is filled with galaxies, stars and planets, much like those we observe. There's no reason to expect dramatically different structures or compositions. The same processes that form the Milky Way, gravitational collapse of gas clouds, star formation, planetary accretion, would have occurred there as well. In this view, the unobservable universe is simply more of the same, extending infinitely in all directions. But here's where infinity creates interesting puzzles. In an infinite universe with randomly distributed matter, every possible configuration of particles must occur somewhere. Not just similar configurations, exact duplicates. This is a mathematical inevitability, not speculation. Given infinite space and finite possible arrangements, repetition is certain. The number of possible quantum states in a region the size of our observable universe is unimaginably large but finite. Estimates suggest roughly 10 to the power of 10 to the power of 120 distinct configurations. That's incomprehensibly many, but it's still finite. In an infinite universe, each configuration must occur infinitely many times, including exact duplicates of our entire observable universe, atom for atom, identical in every detail. This means there are infinite regions, impossibly far away, where everything is exactly the same as here. Same galaxies in same positions, same Earth orbiting, same sun, same you read in these same words right now. Not similar, identical. This isn't science fiction or parallel dimensions. It's straightforward logic applied to infinite space with finite configurations. The distances involved boggle comprehension. One estimate suggests you'd need to travel roughly 10 to the power of 10 to the power of 29 meters, a 1 followed by 10 billion zeros meters, to reach the nearest exact duplicate of our observable universe region. That distance is so large it makes the observable universe seem like a single atom in comparison. But in true infinity, Such distances are negligible. There are infinitely many such duplicates. Does this bother you? It bothers some physicists deeply. It seems to undermine uniqueness, individuality, the specialness of our existence. If there are infinite identical copies of you, in what sense are you special? What does it mean to say I or we when those words apply to infinite exact duplicates scattered through infinite space? Perhaps it helps to remember that these duplicates are causally disconnected. Light from them will never reach you. No information, no interaction, no connection is possible. They exist in a technical sense, but they're irrelevant to your experience, your life, your consciousness. You're still you, living your unique subjective experience, regardless of whether infinite exact copies exist beyond the cosmic horizon. Or perhaps the better response is acceptance. Maybe infinite exact duplicates is simply what an infinite universe implies, and we need to adjust our intuitions about uniqueness and individuality accordingly. Maybe identity is local, defined by causal connections and continuity of experience, not by being the only instance of a particular configuration in all of infinite space. There's also the possibility that the unobservable universe is not just more of the same. If eternal inflation is correct, if we live in one bubble among many, then beyond our bubble lies the inflating background, and beyond that lie other bubbles with potentially different physics. Our observable universe would be part of one bubble, and the unobservable region would first be more of our bubble, then the boundary where our bubble meets the eternal inflation background, then potentially other bubbles entirely. In this picture, the unobservable universe becomes vastly more diverse. Some regions would be similar to ours, governed by the same physics. Other regions, other bubbles, might have different laws entirely, different numbers of dimensions, different particles and forces. Most would be sterile, unable to support complexity. A few might support life and observers like us. The unobservable realm becomes a multiverse of possibilities. We can't know which picture is correct. We can't observe beyond our horizon to test these ideas. What we can do is follow the mathematics and physics where they lead, take seriously the implications of our best theories, and acknowledge when we've reached the limits of observational science. The unobservable universe is a reality we must accept even as we can never directly verify its properties. And this brings us to a deep question. If much of reality is fundamentally unobservable, what does that mean for the scientific method, which relies on testing theories against observations? Can we still do science at the boundary of the observable? Or must we accept that some questions, some aspects of reality, lie forever beyond empirical verification? These are questions that challenge the foundations of how we understand knowledge itself. Science has been extraordinarily successful at revealing the universe's nature. We've measured its age, determined its composition, mapped its large-scale structure, and traced its history from the first fraction of a second to the present day. We can make predictions about its future that extend trillions of years forward in time. This success can create an impression that science will eventually answer all questions, explain all mysteries, reveal all truths. But cosmology, particularly when confronting infinity and the unobservable universe, reveals clear limits to what science can tell us. Not temporary limits that better instruments or clever experiments might overcome, but fundamental limits imposed by the nature of reality itself. And recognizing these limits is important, not as a defeat for science, but as a clarification of what scientific knowledge actually is and what questions it's designed to address. The most obvious limit is observational. We can only detect light and other signals that have reached us. The cosmic horizon is a hard boundary on observation. We cannot see beyond it, no matter how powerful our telescopes become. If the universe is infinite, we can never observe more than an infinitesimal fraction of it. Claims about what exists beyond the horizon cannot be directly verified through observation. This doesn't mean such claims are meaningless or unscientific. We can use theoretical reasoning to extrapolate beyond what we observe. If the laws of physics work the same way everywhere, and all our observations suggest they do, then we can predict what should exist in unobservable regions. We can test the consequences of our theories in the observable universe and gain confidence that those theories apply more broadly. But there's still a gap between what we can test directly and what we must. Infer. Consider the question of whether the universe is infinite. We can measure its geometry and find it's flat or very close to flat. Flat geometry, in standard cosmological models, implies infinite spatial extent. But this is an inference, not a direct measurement. We observe flatness within our horizon and extrapolate to infinity beyond it. It's a well-motivated extrapolation, but it's still an extrapolation. We cannot measure infinity directly. Infinity is, by definition, larger than any finite measurement. Similarly, consider eternal inflation and the 90 minutes. You've been here for 90 minutes, quietly, patiently, choosing this over everything else the world was offering you tonight. Do you know how rare that is? Most people cannot sit with something slow and meaningful for more than a few minutes before reaching for something louder. But not you. Not tonight. This channel exists for exactly this kind of person, and a like and subscribe is how we find more of them. It is how we find each other. Thank you for still being here. Now let's continue. Consider eternal inflation and the multiverse. These ideas emerge from applying our best theories, quantum mechanics and inflation, consistently and following where the mathematics leads. They solve real problems and make testable predictions within our universe. But the claim that other universes exist beyond our cosmic horizon cannot be directly verified. We cannot observe these other universes, cannot receive signals from them, cannot conduct experiments in them. This has led some physicists to argue that the multiverse is not science but metaphysics, speculation that lies beyond the realm of testable hypotheses. Others counter that if the multiverse is a necessary consequence of our best theories, and if those theories are well tested within the observable universe, then we should take the multiverse seriously even if we can't observe it directly. It's a legitimate debate about what counts as scientific knowledge. There's also the question of what happened before the Big Bang, or more precisely, what exists beyond the boundary conditions of our current theories. General relativity predicts a singularity at the beginning, a point of infinite density where our equations break down and physics as we know it ceases to apply. This singularity marks a limit to what current physics can tell us. We need a theory of quantum gravity to describe the earliest moments, and we don't have a complete experimentally verified theory yet. Some approaches to quantum gravity, like loop quantum cosmology, suggest the singularity might be avoided, that the Big Bang might have been a big bounce from a previous contracting phase. Other approaches suggest different possibilities, but these are theoretical speculations, not established science. We're working at the boundary of the knowledge, where mathematics and physical intuition guide us, but where experimental verification remains elusive. Even more fundamental are questions about why the laws of physics have the form they do, why the constants of nature have the values we observe. We can measure these constants with great precision, and we can describe how they determine the universe's behaviour, but we can't currently explain why they are what they are. Is there some deeper principle that requires these specific values? Or are they arbitrary, perhaps set randomly in our bubble universe, while other bubbles have different values? These questions push against the limits of what scientific explanation can provide. Explaining one phenomenon in terms of deeper principles is the hallmark of good science, but the process must end somewhere. Either we reach truly fundamental laws that cannot be explained in terms of anything deeper, brute facts about reality that simply are, or we face an infinite regress of explanations, each level requiring explanation by a deeper level. Recognizing these limits isn't defeatist, it's honest. Science is a method for gaining reliable knowledge about the observable universe through testing hypotheses against evidence. It's spectacularly good at this, but it's not designed to answer every possible question, particularly questions about realms that are in principle unobservable, or questions about why fundamental laws exist rather than not existing. Those questions might have answers, but they're not the kind of answers science can provide through its standard methods. Does this mean we should give up on these questions? Not necessarily. Philosophy, mathematics, and theoretical physics can explore possibilities, map logical consequences, and develop frameworks for thinking about these deep issues. But we should be clear about the status of different kinds of knowledge. Directly observed facts, well-tested theories, theoretical extrapolations, and philosophical speculation all have different epistemic standing. Confusing these categories leads to confusion about what we actually know versus what we're guessing or hoping. The universe reveals itself to us gradually, through careful observation and rigorous theory. But it also maintains mysteries, questions that seem to resist our attempts to answer them definitively. And perhaps that's appropriate. Perhaps the universe is richer, stranger, and deeper than any finite mind can fully comprehend. Perhaps accepting the limits of knowledge is part of understanding our place in this vast, potentially infinite cosmos. Let's turn from the limits of what we can know to what we can predict about the universe's future. While we may never know what lies beyond the cosmic horizon, we can follow the implications of dark energy and accelerating expansion forward in time and see where they lead. The picture that emerges is both beautiful and melancholy, a slow fade rather than a violent end. Begin with the present day. The universe is 13.8 billion years old. Galaxies fill space in every direction, organized into clusters and superclusters separated by vast cosmic voids. Stars are forming in gas clouds, planets are coalescing around young stars. And life exists on at least one small world orbiting an average star in an unremarkable galaxy. The universe is dynamic, active, full of structure and complexity. Move forward 100 billion years. The accelerating expansion has carried most galaxies beyond our cosmic event horizon. An observer in the Milky Way, which has by now merged with Andromeda to form a larger elliptical galaxy, would see only their local group of galaxies against a darkening void. The cosmic microwave background has redshifted into invisibility. No evidence of the Big Bang or the expanding universe remains observable. Cosmology, as a science, would be nearly impossible to develop from scratch. Continue to 1 trillion years forward. Star formation has largely ceased. The gas clouds from which stars form have been exhausted, converted into stars or dispersed. Most stars that exist are low-mass red dwarfs, slowly burning their hydrogen fuel, destined to shine for trillions of years. The massive, bright stars that dominated earlier epochs have long since died, some in supernova explosions, others in quieter endings. Stellar remnants, white dwarfs, neutron stars, black holes, outnumber living stars. Push forward to 10 trillion years. Even the longest-lived red dwarfs are beginning to exhaust their fuel. The universe is growing dark. Fewer and fewer stars remain active. Brown dwarfs, failed stars too small to sustain fusion, drift through the darkness. Dead worlds orbit dead stars. Occasionally, two stellar remnants collide, briefly releasing energy. But these events grow rarer as the universe expands and objects drift farther apart. At 100 trillion years, the stelliferous era, the age of stars, ends. The last stars wink out, their fuel finally exhausted. Galaxies become invisible, dark collections of stellar remnants and planets, detectable only by their gravitational influence. The universe has entered what's called the degenerate era, dominated by degenerate matter, white dwarfs, neutron stars, and black holes. Throughout this immense span of time, these stellar remnants slowly cool, radiating away their residual heat into the expanding void. White dwarfs, once the hot cores of dead stars, cool from thousands of degrees to merely the temperature of the cosmic microwave background. which itself has cooled to nearly absolute zero through the universe's expansion. Everything is approaching the same frigid temperature, a heat death where no temperature differences exist to drive any process. But wait, there's still gravity. Even in a dark, cold universe, massive objects can still fall together, still release gravitational potential energy. White dwarfs in galaxies occasionally collide, briefly blazing with fusion as their collision compresses them. Brown dwarfs capture one another in binary systems. Even planets, drifting through dead galaxies, very rarely collide. These events are sparse, separated by unimaginable gulfs of time and space, but they occur. At 10 to the 15 years, 1,000 trillion years, even these rare events become significant. Computer simulations suggest that over such timescales, random gravitational interactions slowly disintegrate galaxies. Objects in the outer regions are ejected into intergalactic space through close encounters. Objects in the inner regions lose energy and spiral inward, eventually falling into the supermassive black hole at the galaxy's centre. The galaxy evaporates, leaving behind an isolated black hole surrounded by ejected stellar remnants. Now we enter the black hole era, dominated by black holes of various masses, stellar mass black holes formed from massive stars, intermediate mass black holes, perhaps formed from collisions in dense star clusters, supermassive black holes. Once at galaxy centres, now isolated in an expanding void. These black holes seem eternal, unchanging, but they're not. They evaporate. Stephen Hawking discovered in 1974 that black holes emit radiation due to quantum effects near their event horizons. This Hawking radiation causes black holes to lose mass very, very slowly. The process takes an unimaginable amount of time, but it's inexorable. A solar mass black hole takes approximately 10 to the 67 years to evaporate. A supermassive black hole with 1 billion times the Sun's mass takes 10 to the 100 years. These numbers defy comprehension. The current age of the universe, 13.8 billion years, is insignificant compared to these timescales. But in a universe that expands forever, time is unlimited. Wait long enough and even the largest black holes will evaporate, disappearing in final bursts of radiation. At 10 to the 100 years, the black hole era ends. The last black holes have evaporated. What remains? A vastly expanded space containing isolated fundamental particles, electrons, positrons, neutrinos, photons, separated by distances so large that they'll never encounter each other. The universe has reached its final state, a cold, dark, nearly empty void expanding forever, approaching but never quite reaching a state of absolute zero temperature and maximum entropy. This is heat death. The ultimate consequence of the second law of thermodynamics in an eternally expanding universe. All useful energy has been dissipated. No temperature differences exist to drive any process. No stars shine. No planets orbit. No complexity exists. Just isolated particles drifting through an infinite expanding void forever. Is there anything beyond heat death? Some speculative theories suggest that even in this final state, quantum fluctuations might eventually create new structures. Over timescales of 10 to the 10 to the 50 years or longer, random quantum fluctuations might create temporary pockets of lower entropy, regions where complexity briefly emerges before dissolving back into uniformity. These Boltzmann brains, spontaneous temporary conscious entities arising from fluctuations, would vastly outnumber beings like us, who arose through cosmic evolution. But this is highly speculative. Beyond the realm of tested physics. The far future is bleak, but it's also peaceful. The universe doesn't end in violence or catastrophe. It simply fades, gradually and inevitably, into a cold equilibrium. Everything that was bright and complex dissolves into darkness and simplicity. It's an ending without drama, without climax, just an asymptotic approach to stillness. And in a strange way, there's beauty in that inevitability, in the universe following its laws to their natural conclusion, however distant that conclusion may be. We've explored what the universe is, how it began, and where it's heading. And if you've absorbed all of this, you might feel a certain unease or even existential dread. An infinite universe containing infinite duplicates of everything. A far future of cold, dark emptiness. How is this not worse than a simple, finite cosmos with clear boundaries and a definite ending? But let's examine this feeling carefully. What exactly makes infinity, quote, 16, quote, than finitude? What makes heat death, quote, 17, quote, than a big crunch or some other dramatic ending? These judgments rest on assumptions about what makes reality meaningful or comforting, assumptions worth questioning. The idea that infinity diminishes significance assumes that value comes from scarcity or uniqueness. If there's only one you, you're special. If there are infinite duplicates, you're common. Unremarkable. But does value actually work that way? Your experiences, your relationships, your consciousness, these are meaningful to you not because you're the only instance of your configuration, but because you're experiencing them subjectively, right now, from the inside. Consider an analogy. Imagine learning that somewhere in another country, there's someone with exactly your name, who looks similar to you, who has similar interests. Does this diminish your sense of self? Of course not. That person is living their life. You're living yours. The fact that someone else is similar doesn't make your experiences less real or less meaningful. Now extend this to infinite space and infinite duplicates. Yes, they exist, but they're so far away, so completely disconnected from your causal sphere that they're irrelevant to your actual life and experience. Your consciousness is not diminished by the existence of other consciousnesses, even identical ones. You're still you, experiencing what you experience, connected to the people and places that matter to you. Infinity doesn't change that. It's a fact about the structure of space, not a comment on the value of your existence. Similarly, consider the heat death of the universe. It's bleak, certainly, when contemplated as an ultimate ending. But it's also immeasurably far in the future, 10 to the 100 years, a time span so vast that writing it out fully would require more zeros than there are atoms in the observable universe. Between now and then lies all of human history multiplied by trillions upon trillions, eons of potential experience, discovery and growth. Moreover, heat death is not oblivion in the sense of non-existence. It's a state of maximum entropy where no free energy remains to do work. But the universe still exists, space still exists, the particles still exist drifting through the void. It's just that no complex processes can occur. Is this worse than the universe collapsing in a big crunch, crushing everything back into a singularity? Is it worse than simply ceasing to exist? Or is it just different? Another way the story could end. Perhaps the unease comes from a desire for meaning that transcends physical processes. We want the universe to have purpose, to be building toward something, to matter in some cosmic sense. And when physics tells us that the universe will eventually run down, that everything complex and beautiful will dissolve, we feel that meaning has been lost. But this assumes meaning must be cosmically permanent to be real. Consider instead that meaning might be local and temporal. A human life has meaning to the person living it and to those they affect. Even though that life spans only decades in a universe that will exist for eons, a civilization has meaning to its members, even though it will eventually end. Why should cosmic meaning be any different? Perhaps meaning exists in moments, in relationships, in experiences, not in eternal persistence. The universe as science reveals it, possibly infinite, definitely old, eventually running down, is not hostile to meaning. It's indifferent to meaning. The universe doesn't care about our significance or lack thereof. It simply is, following its laws, evolving according to the mathematics of quantum mechanics and general relativity. Whether we find meaning in that universe is up to us, not up to the cosmos, and there's something liberating in this indifference. The universe isn't judging us, it's not testing us. It's not demanding we fulfill some cosmic purpose. We're free to create our own meanings, our own purposes, our own values without cosmic constraints. We can appreciate the universe for what it is, a vast, ancient, beautiful, strange place, without requiring it to validate our existence. Moreover, the universe as revealed by science is genuinely awe-inspiring. We live at a time when stars shine, when galaxies collide and merge, when complexity emerges from simplicity through physical law. We're composed of atoms forged in stellar cores, arranged through evolutionary processes into beings capable of contemplating the cosmos itself. We can observe light from the universe's infancy, predict its far future, and understand the mathematics governing its evolution. This is not worse than ignorance. This is extraordinary. So perhaps worse is the wrong word. Perhaps stranger, or more sublime, or more challenging to comprehend would be better. The universe doesn't fit our intuitive categories, doesn't conform to the stories we tell about beginnings and endings. But that's a problem with our categories and stories, not with the universe. And adjusting our thinking to accommodate reality as it actually is, that's growth, that's wisdom, that's what it means to truly understand our place in the cosmos. There's a remarkable fact about our cosmic moment that's worth contemplating. We live in the era when the universe is observable, when cosmology is possible, when the evidence of the Big Bang and the expanding universe is still accessible. This won't always be true, and recognizing our temporal position, our place in cosmic history, provides a different perspective on questions of meaning and significance. Think about the deep future we discussed earlier. 100 billion years from now, when the accelerating expansion has carried distant galaxies beyond the cosmic event horizon, when the cosmic microwave background has redshifted into undetectability, observers would have enormous difficulty discovering cosmology. They'd see only their local galaxy or galactic merger, surrounded by apparent emptiness. No evidence of other galaxies, no background radiation, no observable expansion. The universe would appear static and isolated. Could such observers develop modern physics? Yes. They could still study planetary orbits, stellar evolution, nuclear physics, quantum mechanics, all the microscopic and local phenomena that don't depend on cosmological observations. But could they discover the Big Bang? Could they determine the universe's age, composition, and fate? It's hard to see how, without the observational evidence that we have access to. We live in a special time, cosmologically speaking. The universe is old enough that complex structures have formed, stars, planets, life, intelligence. But it's young enough that the evidence of its history remains visible. The cosmic microwave background is still detectable. Distant galaxies are still within our observable horizon. We can still see the expansion, measure the acceleration, and reconstruct cosmic history. This is not to say we're at the centre of the universe or that the universe exists for our benefit. We're not, and it doesn't. But we are fortunate to exist when we do, during the era when the universe reveals its secrets most readily. Observers in the far future will have much less access to cosmological truth than we do. We've arrived during the universe's informative age. This temporal privilege extends to the conditions that allow our existence. We live during the stelliferous era, when stars shine and provide the energy for complex chemistry, for planetary atmospheres, for the evolution of life. This era has already lasted tens of billions of years, and it will continue for tens of billions more. But in the context of the universe's total lifespan, potentially infinite, or at least extending to 10 to the 100 years, the stelliferous era is brief. Reach. The time and place where observers reach. The time and place where observers like us can exist is a narrow window in cosmic history and a small fraction of cosmic space. We're not witnessing the typical state of the universe. We're witnessing a temporary, unusual state, one characterized by stars, complexity, and observability. Does this make our observations privileged in some deeper sense? Some versions of the anthropic principle suggest that the properties we observe must be compatible with our existence, simply because observers can only exist where conditions permit observation. We see a universe with stars and galaxies because those are necessary for our existence, not because they're typical of the universe as a whole. This can seem circular or even tautological, but it's actually a profound insight. The universe we observe is not a random sample of all possible universes or all possible states of our universe. It's conditioned by the fact that observers exist here and now. Properties that seem finely tuned, the strength of gravity, the mass of the electron, the rate of expansion, might be explained not by finding some deeper law that requires those values, but by noting that observers can only exist where those values allow complexity. Whether you find this explanation satisfying depends on your philosophical preferences. Some see it as giving up on finding fundamental explanations. Others see it as recognizing an important selection effect in our observations. Either way, it's clear that our ability to observe the universe depends on existing during a particular era, in particular conditions, when observation is possible. This should instill a certain gratitude. We could have existed during the dark eras of the far future, unable to observe the cosmos. We could have existed in a universe that recollapsed before life evolved. We could have existed in a universe where the constants of nature didn't permit chemistry or stars. Instead, we exist here, now, during a golden age of cosmological discovery, capable of observing and understanding the universe's history and structure. And this privilege comes with a responsibility to actually observe, to actually understand, to make the most of our cosmic moment. We can map the cosmic microwave background, measure the expansion rate, detect gravitational waves from merging black holes, and peer back to the first billion years after the Big Bang. Future observers will never have these opportunities. We do. And that's not worse. That's a gift. Understand. We can look up at the night, understand. We can look up at the night sky and recognise that the light from those stars has been travelling for years, or centuries or millennia to reach our eyes. We can contemplate the cosmic microwave background and marvel that we're detecting photons that have been travelling since the universe was 380,000 years old. We can understand the mathematics of general relativity and see how gravity curves space-time. None of this is worse for being temporary, or for existing in a potentially infinite universe. If anything, the temporariness makes it more precious. The infinity makes it more remarkable. Out of all the infinite space and infinite time, we exist here, now, capable of understanding. That's not a curse. That's an astonishing privilege. One of the most remarkable aspects of modern cosmology is the role of mathematics in revealing truths about the universe that we could never discover through observation alone. Mathematics isn't just a tool for calculating. It's a way of accessing reality, of discovering facts about existence that transcend direct sensory experience. And there's a deep beauty in this, a kind of beauty that might help us appreciate the universe we've discovered, even if it's stranger than we initially hoped. Consider how we know the universe is flat. We don't directly measure the curvature of space. We can't see it or touch it. Instead, we measure the temperature fluctuations in the cosmic microwave background and compare them to predictions from mathematical models. The mathematics of general relativity tells us what pattern of fluctuations we should see in a closed universe, an open universe, and a flat universe. We observe which pattern matches reality. The mathematics was there first before the observations. Einstein developed general relativity in 1915. Decades before, we had the technology to test its cosmological implications. Friedman and Lemaitre found solutions describing expanding universes in the 1920s. Before Hubble observed the expansion, the mathematics told us what to look for, And when we looked, we found it. This is not coincidence. This is the deep relationship between mathematical structure and physical reality. Why does mathematics work this way? Why should equations scrawled on paper by humans describe the behavior of galaxies and the curvature of space? This is one of the great mysteries of science. The physicist Eugene Wigner called it, quote, 22, quote. It seems miraculous that abstract mathematical reasoning, with no apparent connection to physical reality, should predict phenomena with extraordinary precision. Perhaps the answer is that mathematics isn't separate from reality. It is reality in some fundamental sense. The universe might be, at its deepest level, a mathematical structure, and what we call physical laws are simply the properties of that structure. In this view, doing mathematics is exploring the logical consequences of the universe's existence. We're not imposing human constructs onto nature, we're discovering necessary truths about how reality must be. Consider the equations of general relativity. They're beautiful in a mathematical sense, symmetric, elegant, expressing profound ideas in compact form, and they describe the universe with incredible accuracy, from the orbit of Mercury to the expansion of space itself. This beauty is not decorative. It's a sign that we've captured something fundamental, that the mathematics reflects deep truth. The same holds for quantum mechanics, for thermodynamics, for cosmology. The most successful theories in physics are also the most mathematically beautiful. This correlation between beauty and truth is not perfect. Nature sometimes surprises us with inelegant solutions, but it's strong enough that physicists use mathematical beauty as a guide in developing new theories. If a theory is ugly, mathematically speaking, that's often a sign it's incomplete or wrong. What does this mean for our question about the universe's nature? It means that when mathematics tells us the universe is likely infinite, that dark energy is accelerating the expansion, that the far future is heat death, we should take these conclusions seriously. They're not wild speculations. They're the logical consequences of well-tested mathematical frameworks applied consistently to observational data. And there's beauty in these conclusions, even if they're unsettling. The idea that the universe is infinite, that space extends forever without boundary, has a kind of sublime grandeur. It's too large for human imagination to grasp, but we can appreciate its vastness through mathematics. We can write down the equations, follow their implications, and understand in an abstract way what infinity means. Similarly, the mathematics of entropy and the second law of thermodynamics has an inexorable quality, a kind of tragic beauty. The universe must increase in entropy, must evolve toward heat death. Not because of any cosmic malice, but because of simple statistical mechanics. More disordered states are more probable than ordered ones. Complexity is temporary. Simplicity is eternal. This is not worse. This is how reality works, revealed through mathematical law. Even the multiverse, if it exists, has mathematical beauty. The equations of inflation combined with quantum mechanics naturally produce eternal inflation and bubble universes. You don't have to add extra assumptions or fine-tune parameters. Just take the mathematics seriously, follow it where it leads, and the multiverse emerges. Whether this means the multiverse is real, or that our mathematics is leading us astray is debatable, but the mathematical inevitability of the conclusion has a certain elegance. For those who find mathematics cold or inhuman, this might not be comforting. Numbers and equations seem distant from the warm, messy reality of lived experience. But for those who've glimpsed the power of mathematical reasoning, who've experienced the moment when an equation suddenly makes sense and reveals some hidden truth about reality, there's a profound emotional satisfaction. Mathematics connects us to something larger than ourselves, to objective truths that exist independent of human culture or belief. The universe revealed by mathematics is stranger than the universe of our intuitions and everyday experience. But it's also richer, deeper, more subtle. It contains infinities and singularities. curved space-time and quantum fluctuations, all described with mathematical precision. We can understand this universe not through direct sensory experience. Our senses evolved to help us survive on a small planet, not to comprehend the cosmos, but through the power of abstract reasoning. And that's beautiful. The fact that human minds evolved in the African savannah can understand the mathematics of black holes and inflation and the heat death of the universe, that's not worse. That's miraculous. We're limited, finite beings who can nonetheless grasp infinity through mathematics. We're temporary beings who can understand eternity. We're local beings who can comprehend the global structure of space-time. This ability, this privilege, is something to celebrate, not lament. Let's locate ourselves precisely in cosmic history. We exist 13.8 billion years after the Big Bang during the Stelliferous era, at a time when dark energy is just beginning to dominate the universe's dynamics. This is neither the beginning nor the end of the story. We're somewhere in the middle, and understanding our position helps frame both what came before and what will come after. The first stars formed approximately 100 to 200 million years after the Big Bang, ending what astronomers call the cosmic dark ages. Before that, the universe contained only hydrogen, helium, and trace amounts of lithium. No carbon, no oxygen, no iron. None of the heavier elements necessary for planets and life. Those elements were created in stellar cores through nuclear fusion and distributed through space by supernova explosions. Our Sun is a third-generation star formed about 4.6 billion years ago from a cloud of gas enriched by previous generations of stars. The Earth, and we ourselves, are made from stellar ash, atoms forged in stars that lived and died before the Sun existed. We are, quite literally, made of star stuff. As Carl Sagan famously noted, this connection to stellar evolution places us firmly within cosmic history, not outside it. This makes now, broadly speaking, the current epoch lasting hundreds of billions of years, the golden age for cosmology. Before this era, intelligence hadn't evolved anywhere we know of. After this era, the evidence will fade beyond detectability. We exist during the window when the universe can be most fully understood by observers within it. Does this mean we're special? Not in a cosmic sense. The universe didn't arrange itself for our benefit. But we are fortunate in our timing. If intelligent life had evolved 10 trillion years from now, during the degenerate era when stars had died, those beings would have far less access to cosmological truth than we do. They might never discover the Big Bang, never know the universe had a beginning, never measure the expansion or the acceleration. We can know these things. We can observe, measure and understand. And we're doing so right now as a species. The Hubble Space Telescope, the Planck satellite, the gravitational wave detectors, the ground-based observatories, all of these instruments are mapping the universe, gathering data, testing theories. We're living through the era when humanity is actively discovering its cosmic context. Future generations might look back on this time with something like nostalgia, the era when you could still see distant galaxies, when the cosmic microwave background was still detectable, when cosmology was an observational science rather than just theoretical speculation based on ancient data. We're living in that era. We're the ones who can look out and see the universe as it currently is, abundant and observable. This temporal position, this cosmic moment, is part of what makes our existence meaningful. We're not eternal. We're not permanent fixtures of the universe. We're temporary inhabitants of a temporary epoch, but that epoch is magnificent, and recognizing that we exist during this particular window of opportunity, during the time when the universe reveals itself most readily, adds a dimension of significance to our observations and our understanding. We're in the middle of the story, witnesses to the universe's most dynamic and observable phase. What a time to be alive! We've covered an enormous amount of ground in this exploration. From the geometry of space to the far future of the universe, from inflation to dark energy to the limits of knowledge. But let's acknowledge directly what might be the most uncomfortable truth of all. There are questions we cannot answer, mysteries we cannot solve, aspects of reality that lie forever beyond our reach. And learning to be at peace with this uncertainty is part of intellectual maturity. What caused the Big Bang? We can trace cosmic history back to the first fraction of a second, when the universe was incredibly hot and dense. But we cannot currently describe the moment of the singularity itself. Our physics breaks down at the Planck scale, where quantum effects and gravitational effects become equally important. Until we have a complete theory of quantum gravity, the origin itself remains mysterious. Some proposed theories suggest the Big Bang wasn't a beginning but a transition, perhaps from a previous contracting phase, or from a quantum fluctuation in a pre-existing space. But these theories are speculative, lacking experimental confirmation. We might never know what, if anything, existed before or caused our universe's beginning. The question might not even make sense. Time itself might have begun with the Big Bang, making quote, _23 meaningless. What is dark energy? We know it exists. We observe its effects in the accelerating expansion. We can measure its density with reasonable precision, but we don't know what it is. This is not worse than having all the answers. This is better. This is reality as it actually is. Partially knowable, partially mysterious, always more subtle than we expect. And making peace with that, finding beauty in both what we know and what we cannot know, is part of becoming wise about our place in the cosmos. Let yourself sit with that uncertainty for a moment. Let the questions remain questions. Let the mystery be mysterious. Not everything needs resolution. Not everything needs explanation. Sometimes the most honest response is, we don't know, and we might never know. And that's okay. That's part of the human condition, part of being conscious beings in a vast universe, part of the story we're living. Astronauts who've seen Earth from space often describe a profound shift in perspective they call the overview effect. Viewing our planet from orbit, a small, fragile sphere against the blackness of space, fundamentally changes how they understand humanity's place in the cosmos. Borders disappear, conflicts seem trivial, the unity and vulnerability of our world become viscerally apparent. This shift in perspective has parallels in understanding cosmology, in grasping our place not just in Earth orbit, but in cosmic history. From space, Earth appears tiny. The International Space Station orbits at about 400 kilometers altitude, and from that vantage you can see the curvature of the planet, the thinness of the atmosphere, the patterns of clouds and continents. The planet is beautiful, swirls of blue ocean, brown and green land, white clouds constantly shifting. But it's also clearly finite, bounded, isolated in the void. Astronauts report feeling a deep connection to Earth, a protective instinct toward this small world that contains everything they know and love, every human being, every living thing, all of history and culture and art. Everything exists on this one planet. And it's so small, so vulnerable to cosmic forces, so dependent on the delicate balance of atmospheric composition and temperature and distance from the Sun. Now extend this perspective cosmically. Earth orbits an average star in the outer regions of an average spiral galaxy. Our galaxy, the Milky Way, contains perhaps 200 billion stars, many with their own planets. The Milky Way is part of the local group, a collection of about 80 galaxies. The local group is part of the Virgo supercluster, which contains tens of thousands of galaxies, and the Virgo supercluster is one of millions of superclusters in the observable universe. Each level of this hierarchy makes Earth seem smaller, more contingent, more improbable. We're not just a small planet, we're a small planet around a typical star in an ordinary galaxy, in a regular supercluster in a vast universe. Nothing about our location is central or special. We're not at the middle of anything. We're out here in the cosmic sticks, residents of an unremarkable corner of an incomprehensibly large whole. This can induce a feeling of cosmic insignificance, a sense that nothing we do matters in the grand scheme of things. If the universe is so vast, if we're so small and temporary, what's the point? Why should we care about our brief lives on this tiny world when all of it will eventually be forgotten? When the heat death of the universe will erase every trace of our existence? This doesn't solve the world's problems, but it provides a framework for thinking about them. The cosmic perspective encourages cooperation rather than conflict, stewardship rather than exploitation, humility rather than arrogance. It reminds us that Earth is the only home we have, suspended in the vastness of space, and that protecting it matters not in a cosmic sense, but in a human sense. Because we live here. Because this is where meaning exists for us. So yes, the universe is vast. Yes, we're small and temporary, but we're also conscious, capable and present. We can observe, understand and appreciate. We can create meaning in a universe that doesn't inherently provide it. We can look at the cosmos with wonder rather than fear, with curiosity rather than dread. That's the gift of the cosmic perspective. Not terror at infinity, but awe at existence. The far future of the universe, as we've discussed, is bleak. Heat death, maximum entropy, cold darkness extending forever, everything complex, everything interesting, everything that creates meaning, all of it eventually dissolves into uniformity and simplicity. This prospect troubles many people. If everything ends, if nothing lasts, what's the point of anything? How can we find meaning in a universe with such a desolate ultimate fate? This question assumes that meaning requires permanence, that value exists only if it lasts forever. But this assumption doesn't hold up under examination. Consider things you value in your own life, a conversation with a friend, a beautiful sunset, a moment of insight or joy. These experiences are temporary, lasting minutes or hours, yet they're meaningful while they occur. The fact that they end doesn't erase their value. A piece of music is a good analogy. A symphony might last 45 minutes. While it plays, it creates beauty, evokes emotion, communicates ideas through sound. When it ends, the sound waves dissipate, the vibrations cease, the physical traces disappear. Yet the symphony was real. It was beautiful. It mattered to the people who experienced it. Its impermanence doesn't diminish its value. In some ways, the temporariness enhances the preciousness of the experience. Now extend this to human life. A human lifespan is temporary, perhaps 70 or 80 years on average, a century if you're fortunate. Every person who's ever lived has died or will die. Every relationship eventually ends through separation or death. Every achievement eventually fades from memory. Yet we don't conclude that human life is meaningless. We find meaning in experiences, relationships, growth, understanding, creativity, love, all of which are temporary. Why should cosmic meaning be any different? The universe has a lifespan of sorts, not a fixed endpoint like a human life, but a progression from high energy and low entropy toward low energy and high entropy. Complex structures like galaxies and stars exist during a particular epoch, the stelliferous era, which will eventually end. But this doesn't make the galaxies less real or the stars less magnificent while they exist. Consider that you, personally, are also impermanent on multiple timescales. Your body replaces most of its cells every 7 to 10 years. The specific atoms that compose you change continuously through metabolism. Your thoughts and memories shift and evolve. Your identity is not a static thing, but a process, a pattern maintained through constant change. Yet you experience continuity, meaning, value, all within this impermanent, constantly changing system. Moreover, the universe's eventual heat death is so far in the future that it has no practical relevance to any choices or experiences in the present. 10 to the 100 years from now, the last black holes will evaporate. But right now, stars are forming, planets are coalescing, life is evolving, consciousness is experiencing. The distant future doesn't diminish the present reality. There's actually something liberating about accepting impermanence. If nothing lasts forever, then every moment becomes more precious, not less. If the universe won't remember us, then we're free to create our own meanings without cosmic judgment. If there's no ultimate purpose imposed from outside, we're free to choose our own purposes, our own values, our own paths. Buddhism has grappled with impermanence for millennia and reached a similar conclusion, that suffering often arises from attachment to permanence, from wanting things to last forever when everything is inherently transient. Accepting impermanence, accepting that all phenomena arise and pass away, leads not to despair but to a deeper appreciation of the present moment. Perhaps the heat death of the universe is even aesthetically appropriate, a kind of cosmic closure. The universe begins in a singularity of maximum density and minimum entropy. It expands, cools, and evolves toward a state of minimum density and maximum entropy. There's a symmetry to this, a completion of the story arc. Everything that can happen in between, stars, galaxies, life, consciousness, happens during the middle chapters. The ending is a return to simplicity after the temporary complexity of existence. You don't read a book and lament that it ends. You appreciate the story it tells from beginning to end. You don't listen to music and wish it would play forever. You appreciate the composition, the development, the resolution. The universe is similar. It has a beginning, a middle, and an ending. We're living in the middle, experiencing the universe's most interesting phase. That's not worse because there's an ending. That's simply the structure of the story. So when you contemplate the far future, the heat death, the dissolution of everything complex into cold simplicity, try to see it not as a tragedy, but as an ending, appropriate, inevitable, completing the cosmic narrative, and then return your attention to the present, to the middle of the story, to the time when stars shine and consciousness exists and understanding is possible. This is when meaning happens. This is when value is created. This is when we're alive, and that's enough. We've covered the geometry of space, the expansion of the universe, inflation, dark energy, the far future, and questions of meaning and significance. But let's pause and appreciate something remarkable. You, a human being, can understand these concepts. You can grasp infinity abstractly, comprehend timescales of billions of years, follow the logic of general relativity, and contemplate the heat death of the universe. This capacity for understanding is itself extraordinary. Think about what understanding requires. Your brain, composed of approximately 86 billion neurons connected by trillions of synapses, is processing sensory information, forming patterns, creating models of reality. These models are remarkably accurate. They predict observations, make sense of data, unify diverse phenomena under common principles. Your brain is, in a very real sense, simulating the universe, creating an internal representation that corresponds to external reality. And it does this despite being a product of evolutionary processes that selected for survival and reproduction, not for comprehension of cosmology. Your ancestors needed to track prey, avoid predators, recognize kin, navigate social hierarchies. They didn't need to understand the Big Bang or the curvature of space-time, yet somehow the brain that evolved for those mundane tasks can also comprehend the cosmos. This is not something evolution directly selected for. It's an emergent property, a byproduct of general intelligence that proved useful for immediate survival. And possibly, though we don't know, we might be the only beings in the observable universe with this capacity. The universe might be teeming with life, or we might be alone. We simply don't know. But either way, consciousness and understanding are rare phenomena. Most of the universe consists of unconscious matter following physical laws without awareness or comprehension. You are different. You are matter that knows it exists, that contemplates its own nature, that asks questions about origins and endings. This capacity comes with a certain responsibility. If we're among the few, perhaps the only, conscious beings in the observable universe, then understanding the cosmos matters. It's not just an intellectual curiosity, it's a cosmic significance. We're how the universe understands itself. We're the means by which 13.8 billion years of cosmic evolution becomes aware of its own history. But the capacity for understanding is also a gift simply in its own right, regardless of any cosmic significance. Understanding brings satisfaction, a deep intellectual and emotional fulfillment. When you grasp a difficult concept, when the mathematics suddenly make sense, when disparate observations click into a unified framework, when you see how the pieces fit together, there's a joy in that moment. It's one of the distinctive pleasures of being human, and that pleasure is available to you right now in this moment as you follow this exploration of cosmology. You're not just passively receiving information, you're actively comprehending, building mental models, asking questions, making connections. Your neurons are firing in patterns that correspond to reality, creating understanding where there was only ignorance before. This process, this transformation from not knowing to knowing, is deeply satisfying. Moreover, understanding connects you to the long chain of human inquiry that extends back to the first person who looked up at the night sky and wondered what those lights were. Every culture has created stories about the cosmos, mythologies to explain the sun and moon and stars. But science goes beyond mythology. It tests hypotheses, refines models, builds on previous discoveries. You're the beneficiary of thousands of years of accumulated knowledge, standing on the shoulders of countless thinkers who contributed pieces to the cosmic puzzle. When you understand general relativity, you're accessing Einstein's insights. When you grasp the Big Bang, you're building on Hubble's observations and Friedman's mathematics. When you contemplate dark energy, you're engaging with discoveries made only decades ago by observers studying distant supernovae. You're part of a collective human project of understanding, spanning generations and cultures, all working to answer the same fundamental questions. What is the universe? How did it begin? How will it end? What are we? This gift of understanding is available to anyone willing to engage with these questions. You don't need to be a professional physicist or mathematician. You need curiosity, patience, and willingness to grapple with difficult concepts. The universe reveals itself to those who pay attention, who ask questions, who think carefully about observations and their implications, and the satisfaction of understanding is available to all who seek it. So appreciate this capacity you possess. Appreciate that your brain can simulate the cosmos, that your thoughts can range across billions of light years and billions of years, that you can grasp abstractions like infinity and entropy and space-time curvature. This is not worse than ignorance. This is an extraordinary privilege, one of the defining characteristics of being human. We can understand, we can know, and that knowledge, that understanding, is itself a form of meaning, a value that persists as long as consciousness exists to appreciate it. We've journeyed through the geometry of space, the history of the universe, the limits of knowledge, and questions of meaning and significance. We've confronted infinity, contemplated heat-death, and explored the boundaries of what we can know. Now, as we approach the end of this exploration, let's gather these threads together and consider what it means to live with the universe as science reveals it, not as we might wish it to be, but as it actually is. The universe is likely infinite in spatial extent. This is unsettling to contemplate, challenging our intuitive sense of boundaries and finiteness, but infinity is simply a property of space, a consequence of its flat geometry. It doesn't diminish our significance or make our experiences less real. It's a fact about the structure of reality, no more threatening than the fact that the universe is very old or very large. Living with infinity means accepting that there are aspects of reality we'll never observe, regions of space forever beyond our cosmic horizon. It means recognizing that if space is truly infinite, then everything that can happen does happen somewhere, including exact duplicates of our entire observable universe region. These duplicates exist but are causally disconnected from us, irrelevant to our daily lives and experiences. We can acknowledge their theoretical existence without being troubled by it. The universe had a beginning approximately 13.8 billion years ago, emerging from conditions we don't yet fully understand. This beginning doesn't require a supernatural explanation. It might be an inevitable consequence of quantum mechanics and gravity, or it might emerge from some earlier state we haven't yet discovered. Either way, the Big Bang is a fact, supported by overwhelming observational evidence. We can study its consequences without needing to explain its cause, while continuing to investigate deeper explanations. The universe is expanding, and this expansion is accelerating due to dark energy. This acceleration will continue into the far future, eventually carrying most galaxies beyond our cosmic horizon, leaving future observers with a much emptier, darker view of the cosmos than we currently enjoy. We're fortunate to live during the era when the universe is most observable, when evidence of the Big Bang and the expanding universe remains accessible. The universe will eventually reach a state of maximum entropy, heat death, where no complex processes can occur. This is not a catastrophe or a tragedy. It's simply the consequence of the second law of thermodynamics applied over vast timescales. It's so far in the future that it has no relevance to any choices or experiences in the present. Between now and heat, death lies more time than the current age of the universe multiplied by trillions, eons of potential experience and discovery. Living with these facts means adjusting our intuitions about significance and meaning. We're not the center of the universe. There is no center. We're not permanent. Nothing is. We're not cosmically significant in the sense of the universe existing for our benefit, but we are conscious, capable of understanding, able to appreciate beauty and create meaning. These capacities are real, valuable, and sufficient. The universe revealed by science is stranger and vaster than the universe of human intuition, but it's also more interesting, more sublime, more worthy of awe. A finite, human-scale cosmos might be more comfortable, but it would be less magnificent. An infinite universe, one containing unimaginable numbers of galaxies and stars, one extending far beyond what we can ever observe. This is genuinely grand, far beyond human pretension or ambition, and we can understand this universe. Not completely, not in every detail, but substantively. We can measure the expansion rate, determine the age, map the large-scale structure, predict the far future. We can build instruments that detect photons from the universe's infancy, gravitational waves from merging black holes, neutrinos from stellar cores. We can develop mathematical frameworks that describe reality with extraordinary precision. This capacity for understanding is our distinctive gift, our cosmic role. Living with the universe as it is also means accepting uncertainty and mystery. We don't know what dark energy is. We don't know what happened before the Big Bang or if quote_25 even makes sense. We don't know whether the multiverse exists or what lies beyond the cosmic horizon. These gaps in knowledge are not failures. They're the current boundary of understanding, the frontier that future discovery might push back. Some questions might be permanently unanswerable, and that's okay. Mystery preserves wonder. Perhaps most importantly, living with this universe means recognizing that meaning is something we create, not something we discover in the objective structure of the cosmos. The universe doesn't provide meaning. It provides atoms, physical laws, space and time. We arrange these raw materials into lives, relationships, purposes, values. The universe's indifference to our meanings doesn't make them false or trivial. It makes them ours, freely chosen, genuinely created. You're an arrangement of atoms that has become conscious, that can contemplate the cosmos, that can appreciate beauty and understand mathematics and experience love. This arrangement is temporary. Eventually you'll die, and the atoms will disperse, and the pattern that was you will dissolve. But while the pattern exists, it's real. Your experiences are real. Your understanding is real. Your meanings are real. The eventual ending doesn't erase the present value, so live with the universe as it is. Infinite in space, finite in age, expanding toward heat death, governed by physical laws, indifferent to human purposes. This is not worse than comforting myths. Before I say goodnight, I need you to know something. When this video was posted, most people scrolled right past it. They saw the length, they saw the topic, and they kept scrolling. But you didn't. You stayed for 2.5 hours, you chose depth over speed, and wonder over noise, and I think that says something beautiful about the kind of person you are. If this channel has given you something tonight, a little more peace, a little more wonder, a little more understanding of the world you live in, then a like and subscribe is the kindest thing you can leave behind before you sleep. Not just for this channel, but for the next person out there tonight who needs exactly what you just found here. Now, rest. You have earned it. This is not worse than comforting myths or wishful thinking. This is reality, revealed through centuries of careful observation and rigorous theory. And reality, properly understood, is magnificent. Look up at the night sky when you can. Recognize that the light from those stars has been travelling for years or centuries or millennia. Understand that you're seeing the universe as it was in the past, that the present moment is different for every observer, that simultaneity is relative. Appreciate that the matter in your body was forged in stellar cores, that you're intimately connected to cosmic processes. Feel the rotation of the Earth beneath you, carrying you eastward at about 1,000 miles per hour at the equator. Feel the Earth's orbit around the Sun, moving at about 67,000 miles per hour. Feel the Sun's orbit around the galactic centre, moving at about 500,000 miles per hour. You're in motion through space at tremendous speeds, part of a cosmic dance that's been ongoing for billions of years. And know that you're capable of understanding all of this. Your brain, evolved for survival on an African savanna, can nonetheless comprehend the cosmos. This is not worse because the universe is infinite, or because it will eventually run down. This is extraordinary. You are extraordinary. Not cosmically special, but humanly remarkable. And that's enough. That's more than enough. That's everything. We've travelled together for 2.5 hours, exploring one of the most profound questions we can ask. Where, or if, the universe ends. We've journeyed from the comfortable cosmos of crystalline spheres to the infinite, expanding, accelerating universe revealed by modern cosmology. We've confronted infinity, contemplated heat death, and explored what these discoveries mean for how we understand our place in existence. From the early observations of Edwin Hubble that revealed the universe's expanding, to the cosmic microwave background that confirmed the Big Bang, to the precise measurements that showed the universe is flat and therefore likely infinite, to the shocking discovery that expansion is accelerating, each step has revealed a cosmos stranger and grander than we imagined. Not worse, just different from our intuitive expectations. The answer, as honestly as I can give it, is this. The universe probably doesn't have an edge in space. If it's flat, which observations suggest, then it extends infinitely in all directions. But it does have edges in time. It began approximately 13.8 billion years ago, and it will continue expanding into an incomprehensibly distant future. It has an edge in observability, the cosmic horizon beyond which we cannot see, which will actually shrink in the future as acceleration carries distant galaxies beyond reach. Perhaps the answer is that asking where the universe ends is asking the wrong question. The universe isn't the kind of thing that ends in the way we intuitively imagine, with a boundary or wall. It's more subtle, more strange. It's infinite but bounded by horizons. It's eternal but had a beginning. It's comprehensible but contains mysteries. These apparent contradictions resolve when we think carefully about the geometry of space and time, but they resist simple intuitive answers. And maybe that's appropriate. Maybe the universe should challenge our intuitions, should be larger and stranger than our everyday experience prepares us for. Maybe encountering this strangeness and learning to understand it anyway is part of what makes us human, part of what distinguishes us as the species that asks these questions and works to answer them. If you've stayed with me this entire journey, thank you. 2.5 hours is a significant investment of time, and I'm grateful you've chosen to spend it exploring these ideas. I hope you found beauty in the mathematics, wonder in the observations, and perhaps some peace in the philosophical implications. The universe is what it is, and understanding it, really understanding it, is one of the great privileges of being conscious. Wherever you are in the world right now, in a darkened bedroom, a quiet corner, a peaceful space where you can finally rest, I hope you're comfortable. I hope your breathing has slowed, that your thoughts have quieted, that your body feels heavy and warm. I hope the concepts we've explored, challenging as they might be, have given you something to contemplate, something to appreciate, maybe even something beautiful. Look up at the night sky if you can, or imagine it if you can't. All those stars, each a sun like ours, some with planets, possibly with life, possibly with beings who are also looking up at their night sky and wondering about their place in the cosmos. And beyond those stars, the galaxies, hundreds of billions of them in the observable universe, each containing hundreds of billions of stars. And beyond the observable universe, if the geometry is what we think it is, infinite space extending forever, filled with infinite galaxies we'll never see. It's too vast to truly comprehend. The human mind can't hold infinity. But we can gesture toward it, can understand it mathematically, can appreciate it abstractly. And there's something deeply satisfying in that, in pushing our understanding to its limits, in grasping what we can grasp of a reality far larger than ourselves. You're part of this infinite cosmos, made of atoms forged in stellar cores, arranged through evolutionary processes into a conscious being capable of contemplating infinity itself. You're temporary, yes, but you're real. You exist right now in this moment, experiencing what you're experiencing, and that's not diminished by the universe's vastness or by its eventual heat-death trillions of years hence. That's magnificent in its own right, so rest now. Let go of the questions, the mathematics, the vast timescales and cosmic distances. Return to the simple fact of your own existence, your own breathing, your own immediate experience. The universe will continue expanding whether you think about it or not. The galaxies will continue their recession. The dark energy will continue driving acceleration, and the far future will unfold according to physical law. None of that requires your attention or your worry. Sleep well. Dream of stars if you dream at all, or of nebulae where stars are born, or of the cosmic microwave background carrying messages from the universe's childhood. Dream of infinity if you can, or of the heat death of the universe, so distant it might as well be forever. Or dream of nothing at all, letting your consciousness rest from its contemplation of the cosmos. Thank you for this journey. Thank you for your curiosity, your attention, your willingness to contemplate difficult questions and strange answers. The universe is vast and strange and beautiful, and I'm glad we could explore it together. Good night.